Hello there and welcome to A2 Maths on Specimen Paper 1, and here we're looking at question 13, a trigonometry question. So part A is express 2 sine theta minus 1.5 cos theta in the form r sine theta minus alpha, blah blah blah, alpha to 4 decimal places. So let's get started on the r sine theta minus alpha part. When we expand this using the trigonometry identities in the formula booklet, we get r bracket sine theta cos alpha minus cos theta sine alpha. And then, when we expand the brackets with the r, we get r. I'm going to reverse the order of some of these multiplications just for future referencing. R sine alpha cos theta. Okay, so now let's compare with what we're trying to show this is equal to. We're trying to show that this is equal to 2 sine theta minus 1.5 cos theta. Okay, so we can clearly see then the thing that's in front of the sine theta is 2, or on the other side it's r cos alpha. So therefore 2 must equal r cos alpha. And the thing that's in front of the cos theta is r sine alpha. So 1.5 must be r sine alpha. Okay, so now we've got two simultaneous equations with two variables that we need to now work out. The first way that we can solve these is by doing equation 2 divided by equation 1. That will give us r sine alpha over r cos alpha equals 1.5 over 2. And then when we simplify this, we actually get tan of alpha equals 1.5 over 2. So therefore alpha, if we work that out on the calculator, gives us 0.6435. Great. So that's one variable that we've found. Now to get an exact value for r, a good way of doing this is to do 2 squared plus 1 squared. Well, this seems a very difficult way of doing it, but let me show you why this is a really good way of doing it. Let's do the r squared sine squared alpha plus r squared cos squared alpha. That's what you get when you square the right-hand side of equation 2 and add it to the square of the right-hand side of equation 1. This is going to be equal to 1.5 squared plus 2 squared. What do we then get? Well, sine squared plus cos squared equals 1, so when we factorise out r squared, it would just be r squared times 1, so therefore r squared is equal to the 1.5 squared plus 2 squared, 1.5 squared plus 4, that's equal to 25 over 4. And then when we take the square root of it, it's going to give us 5 over 2, or in other words 2.5. So therefore what we can say is that 2 sine theta minus 1.5 cos theta is identical to 2.5 sine theta minus 0.6435. So there we are, that's the answer to part A then. Hopefully you've done tons of these, at least 20 of these types of questions, and you're really familiar with them now, and you can just do them in your sleep really. Okay, moving on to the contextualised part of the question then. So Tom models the depth of water d meters at Southview Harbour on the 18th of October 2017 by the formula d equals 6 plus 2 sine 4 pi t by 25 minus 1.5 cos 4 pi t over 25, where t is the time in hours after midnight on 18th of October 2017. Use Tom's model to find the depth of the water at 0000 hours. So what that means is just plug in t equals 0. So d is going to equal 6 plus, now when time is 0, this value inside the sine function here is just going to be 0. And then when t is 0 here, the value inside the cos function is going to be 0. Cos of 0 is 1, so it's going to be minus 1.5. So the answer there is 4.5. So the answer to part B is 4.5. part C, the maximum depth of the water. Now this is where we have to bring in the answer to part A. So the answer to part A is going to bring in for us, it's going to be 6 plus, because there is a 6 plus there already, 2.5 sine theta minus, it's going to be 0.6435, and that theta is representing this 4 pi t over 25. In fact, it would be a good idea to write that in so it all looks nice and neat and tidy. Sine 4 pi t over 25 minus 0.6435. Now, what are we answering here? Now, we're answering part C, which is find the maximum depth of the water. We want to find the maximum depth of the water, therefore the sine function has to be at its maximum as well. When the sine function is at its maximum, no matter what transformation we have inside the bracket, the maximum the sine function can be is 1. So therefore 6 plus 2.5 times 1, the answer there is 8.5 meters. The answer to D, find the time in the afternoon when the maximum depth of water occurs. So this is in the afternoon, so T has to be a value in between 12 to 24. This is probably going to be in radians mode. Okay, so a pretty tricky question this. So what we want is for the value that's inside this bracket here to equal a point at which the sine function will equal its maximum value. So let's just draw a graph on this first. So it's going to be start from there, up, down, there, up, down, there, up, down. So the maximum values are going to be when we have either pi by 2, 5 pi by 2, or 9 pi by 2. It's probably going to be one of these. We could carry on if it's not one of those, but it's probably going to be one of these. Let's pick the 5 over 2 value first. So what we're going to do then is we're going to set 4 pi t over 25 minus 0.6435 to be equal to 5 pi by 2. Now I'm going to do all the rearranging on my calculator here. So this is going to give us, starts with writing out 5 pi by 2, so 5 pi by 2. And then we're going to add this 0.6435 onto the other side, 6435. And then we're going to multiply by the 25 times 25, and then divide by 4 pi, and we get a value that is 16.905. So here t is the value 16.905. So find the time in the afternoon, so take away 12 from this and set it into time mode. So let's take away 12 and then put it into time mode. That's going to be at 4:54 p.m. in the afternoon. Lovely. So there we are. The last part of this question is part E. So by considering the depth of water at 00 hours on the 19th of October, so it's ever so slightly different. We've now got X's here. Jolene attempts to use a similar model in order to find the depth of water at South Bank on the 19th of October 2017. Jolene uses the model by the formula of this thing here. Pretty sure that's exactly the same as it was before. By considering the depth of the water at 00 hours for both models, explain why Jolene's model is not correct. Well, it looks exactly the same thing as it did before. An attempt to find... So it's going to be exactly the same as Tom's model. Because nothing's changed from Jolene's model to Tom's model. Okay, so now part 2, hence find a suitable model for H in terms of T. Well, what it should be really is if we consider Tom's model, which was this one here, at t equals 24. So after 24 hours have passed, it won't be the 19th of October anymore, it will be Jolene's day, which is the 19th of October. So what we're going to do then is we're going to plug in 24 into this expression here, and I expect the 6 at the front here is going to need to change. So plugging in h of 24, we're going to get 6 plus 2 sine 4 pi times 24 over 25 minus 1.5 cos 4 pi x over 25. Whoops, not x, we need to type in 24 at that point there. So what we're going to get when we type in 24, let's just do it really quickly, it's going to be 6 plus 2.5 times sine of 4 pi times 24 divided by 25, and then minus 0.6435. We're going to get 3.722. But remember, the height at time 0 is 1.5, so we now need to add on 1.5 onto this for the fact that we are going to be subtracting this value here on Jolene's time anyway. So add 1.5 and we get 5.22. So therefore, what this says is that the height of Jolene's model should be starting at 5.22 on the constant of addition there. So it should be 5.22 plus 2 sine 4 pi x over 25 minus 1.5 cos 4 pi x over 25. That's what it should be. It should be 5.22 at the front there, because that will help it match up with Tom's model and Jolene's model by the fact that 24 hours after Tom has done his model, the depth of the water should match up with Jolene's model. The reason we've had to add on 1.5 there is because when we plug in 0 into Tom's model, we had to take away 1.5 to get the substituted 0 value of 4.5, which will give us then 6. So then we need to do the reverse of that, which is to add 1.5 to get it at 5.22, so that then when we type in h of 0 here, we're going to have 5.22 take away 1.5, which gives us the 3.722 depth there. Yeah, so that's basically it then. So that needs to be Jolene's model. So there we are. That's a really tricky question 13 there. 11 marks for it. Very well done if you did get that, but I understand perfectly well if you've needed to come and have a look at the video on how to do that one. So there we are. That's the answer to question 11 there. Probably a better answer to part E is that the end of Tom's model does not match Jolene's model. Okay, so there we are. That's probably a better answer for part I there. 11 marks, that's question 13. Let's now move on to question 14.